Hi, good morning, my dears. I welcome you for the today's session about Langevien theory for diamagnetism or classical theory for diamagnetism. So this is today's our session. In the previous session, we discussed about what is magnet and the types of magnets and classification of magnets we discussed in the previous session. In the classification of magnetic materials, one of the important magnetic material is diamagnetic material. We also know that a diamagnetic material, as for yesterday's session, diamagnetic material is a magnetic material which is which is feebly repel in the presence of actional magnetic field. In the presence of actional magnetic field, a material or a specimen which is weakly or feebly repel in the presence of actional magnetic field, that material is defined as diamagnetic material. Diamagnetic material relate to permeability. We also know that diamagnetic material relate to permeability is less than unit. That means it is less than to 1. Also, the susceptibility of diamagnetic material is defined as small and negative. What is that? Small and negative. This is about the susceptibility of the diamagnetic material. So here diamagnetic material susceptibility is what? Susceptibility is what? Small and negative. And coming to the relative permeability, the relative permeability is mu r is very less than 2 unity. That means less than to 1. So these are the characteristics of the diamagnetic material. So diamagnetic material, whatever characteristics it is possessed, these all are called diamagnetism. What is that? Diamagnetic material and their characteristics all defined as diamagnetism. We also know that one. What are the examples of the diamagnetic material? The examples of the diamagnetic material with our daily activity elements I have considered as the drinking source of organism. It may be human being or it may be plantation, anything. The drinking source of everything is what? The drinking source of water. That means H2O is the one of the example. What is that? H2O, the drinking source of organisms. That is H2O is an example of the diamagnetic material. Not only that one, and here on a paper to draw a diagram we are using a pencil. The chemical compound of pencil or the crude form of the pencil is nothing but what? Graphite. So graphite is another example. I am giving 3 examples for the diamagnetic material. So the first one is what? Water. The second one is what? Graphite. And coming to the third one, the cooking source of the element, that is salt of element, sodium chloride. So here the drinking source of humans or organisms, what is that? Water. And writing source of the pencil is what? Graphite. And cooking source of the material is what? Sodium chloride. So here H2O, sorry, H2O and graphite, H2O, graphite and sodium chloride are the examples of the diamagnetic materials, or the examples of the diamagnetic material. So the Langevin theory is proposed by who? So the Langevin, so coming to the theory. So the Langevin theory, this theory is proposed by the Paul Langevin in the year of 1905. In the year of 1905, in the year of 1905, Paul Langevin in the year 1905, 19th century 5, he introduced this theory to analyze the theory of the diamagnetism. The theory of diamagnetism. In the year is what? That is 1905. Let's see, before we are moving to this concept, we want to know what is the exact relation between magnetization M and susceptibility chi. Let's see. Magnetization is defined as a magnetic moment per unit volume. What is that? A magnetic moment per unit volume. What is magnetization? Magnetization M is defined as magnetic moment per unit volume. Magnetic moment per unit volume. For a certain magnetic material, for a magnetic material, it is found that the magnetization M is proportional to the magnetic field strength. So in magnetic material, it is found that one. What is found that? It is found as magnetization M is proportional to magnetic field strength H. Magnetic field strength H. So M is proportional to the H. So what is magnetization? Magnetization is defined as magnetic moment per unit volume. What is that? Magnetic moment per unit volume. But in some magnetic materials, not some, in magnetic materials, it is found that the magnetization M is proportional to magnetic field strength H. The magnetization M is proportional to magnetic field strength H. Therefore, M is proportional to H. In the position or in the place of proportionality, if you consider equal symbol, then a constant will be arise, that is nothing but chi. So therefore, M is proportional to H, M equal to chi H, where chi is the magnetic susceptibility. What is that? Magnetic susceptibility. M is magnetization, H is magnetic field strength. So here, in terms of the susceptibility, what is paramagnetic material? Possess character, that is paramagnetism. What is diamagnetism material? So there is a double I is present here. This is one single I. So here, if the susceptibility of any material, if it is greater than 0, that material is defined as paramagnetism. If the susceptibility of any material is less than 0, it is less than 0, it may be negative. If it is less than 0, then it is what? It is diamagnetic material. So if it is greater than 0, what is greater than 0? If the susceptibility is greater than to the 0, that is paramagnetism. If the paramagnetic material, that is paramagnetic material, and the characteristic is called paramagnetism. If the susceptibility is less than to 0, that material is called diamagnetic material, and its characteristics is what? Diamagnetism. So just now already we discussed here. Once again I will explain to you. A diamagnetic material, when placed in the presence of the action of magnetic field, what is that? A diamagnetic material, when placed in the presence of action of magnetic field, it weakly magnetizes, means feebly repel opposite to the applied field direction. That means here, in other way, it can say that it weakly magnetized opposite to applied field direction. Opposite to applied field direction. The susceptibility of diamagnetic material is what? The susceptibility of, already we discussed this one. The susceptibility of diamagnetic material is small and negative. What is that? The susceptibility of diamagnetic material is small and negative. Not only that one, the susceptibility is also independent of temperature. The susceptibility is also independent of temperature. Not depends on temperature. It is independent on temperature. So this is about the susceptibility. The susceptibility of diamagnetic material is what? It is small and negative. Coming to the another one. So how we are going to explain this Langevin theory? So right now, just now we discussed, up to now we discussed about the diamagnetic material characteristics. Now, this diamagnetic material characteristics or this diamagnetic material diamagnetism in terms of Langevin is what? That is about Langevin theory or classical theory for the diamagnetism. Let's see. Let us consider a revolving electron in an orbit. What is that? Let us consider an electron in an orbit. In an orbit constitutes, what that constitutes current in the orbit. Current in the orbit. Let us consider a revolving electron in an orbit, which is considered in an orbit. It constitutes or it is having current. This is what? Current, electric current. It is having electric current in the orbit. Electric current in the a revolving electron. So this is the orbit. In this orbit, whatever electron is there, that electron is revolving. So the revolving electron is consist of what? It is consist, the revolving electron is consist electric current. Sorry, this is double current. Current is not, this is electric current. This is what? Electric current. They a revolving electron which is revolving in the orbit is consist or it constitutes electric current in the orbit. This electric current, what doing? This electric current produces magnetic field perpendicular to the plane of the orbit. So here, whatever electron is revolving in an orbit, so this electron is consist or constitutes electric current. What is that? It constitutes electric current. So this electric current is what doing? This electric current produces, what is doing? Produces magnetic field. Produces magnetic field perpendicular to whom? Perpendicular to the plane of the orbit. Perpendicular to the plane of the orbit. So here the revolving electron is constitutes, it consists electrical current. This electric current in the orbit, in an orbit, produces magnetic field, and this magnetic field is perpendicular to whom? This magnetic field is perpendicular to plane of the orbit. It is perpendicular to whom? Plane of the orbit. The electrons in an atom, the electrons in an atom are revolving in different orbits. The electrons in an atom are revolving in different orbits oriented in random directions. So here, whatever electron is revolving in an orbit, this electron or these electrons in different orbits oriented in random direction. They are oriented in random direction, not in order direction. They are in order direction. So they orient in different orbit. They oriented in random direction. That means it may be anti-clockwise or clockwise. That means clockwise as in anti-clockwise. What is that? Clockwise as in anti-clockwise. So here there are different orbits oriented in a random direction. That means clockwise as in anti-clockwise. So what is happening? So here that is clockwise, anti-clockwise. So what is happening? The net dipole moment is what? if it is a positive and this is negative, so positive and negative, so the net dipole moment is what? The net dipole moment is 0. So the sum of the magnetic moment produced by all these electrons, the sum of magnetic moments produced by all these orbiting electrons in an atom is what? 0. Why? Because one is clockwise, the another one is anti-clockwise. That means clockwise and anti-clockwise, they are randomly oriented. Because of this particular reason, the net magnetic moments produced by all these orbiting electrons in an atom is what? It is 0. The angular velocity of an electron in an orbit of radius, sorry, this is must be smaller. The angular, so this is must be smaller. The angular velocity of an electron, the angular velocity of an electron in an orbit of radius r is what? It is omega naught. The angular velocity of an electron in an orbit of radius. What is the radius of orbit? That is small r. And what is the angular velocity? The angular velocity is omega naught. Before applying the magnetic field, the angular velocity is what? Omega naught. The angular velocity is what? Omega naught. The current in the orbit is considered. So here, after applying the magnetic field, the current in the orbit is considered. So the electric current is what? The electric current in the orbit is considered as, so we have an equation. The revolving electron is having, that is I equal to, what is that? I equal to minus E, sorry, I equal to minus E omega naught by 2 pi. What is that? I equal to minus E omega naught by 2 pi. So here I equal to, the electric current in an orbit is what? I equal to minus E into omega naught by 2 pi. What is omega naught? Omega naught is nothing but angular velocity. 2 pi is nothing but particular phase. Minus E what? Why minus E? That is induced effect which is comes from Langevien, which is considered from Langevien. I equal to minus E into omega naught by 2 pi. After further simplification, it is I equal to minus E omega naught by 2 pi, minus E into omega naught by 2 pi. So minus E into omega naught by 2 pi, minus E omega naught by 2 pi. This is about the equation of current in an orbit. The current in the orbit is what? I equal to minus E omega naught by 2 pi. The magnetic moment due to the orbiting electron. So after the current, what is the next one? The magnetic moment due to the orbiting electron. So the magnetic moment due to the orbiting electron is what? That is mu L is IA. That is what? Mu L equal to IA. What is that? Mu L, the magnetic moment, is equal to IA, where I is the current, A is the area. A is the area. So A is what? That is pi r square. So here I equal to, you replace the value of I here. I equal to is what? From the previous slide, I equal to minus E omega naught by 2 pi into pi r square. So where A is the area. So here you replace the value of I. What is I? Minus E omega naught by 2 pi, where A is what? A is pi r square. After simplification, it is minus E omega naught by 2 pi into pi r square. For the simplification, so what is the further simplification? So you can see here pi, in the further simplification, pi and pi will be cancelled. Then what you will get? So that is minus e omega naught r square by 2. What is that? Minus e omega naught r square by 2. So this is about whom? This is about the magnetic moment value, the orbiting electron. Magnetic moment. The magnetic moment due to the orbiting electron is what? Mu L equal to minus e into omega naught into r square by 2, where A is the area inside the orbit, which is pi r square. So we need to consider again two figures here, figure A, figure B. From figure A, what we can analyze, electron revolving in an orbit, electron revolving in an orbit of radius r around a nucleus in the absence of external magnetic field. So this is a figure about in the absence of external magnetic field, the electron, revolving of electron. What is that? A revolving of electron in the absence of external field. Coming to the figure B, this is figure B. So what is figure B? Electron revolving in an orbit of radius r around a nucleus in the presence of applied magnetic field. In the presence of applied magnetic field. So in the presence of applied magnetic field is what? You can see there are some type of, due to this applied field, there is a force generated, that is a magnetic force, and there is a orientation in the electron. You can see positive character or positive E, negative E we consider here. So there is the orientation of electron is changing when you apply the external magnetic field, and because of this external magnetic field a force also generated, that is nothing but Fb. So from figure A, figure B, what we can analyze? From the figure A, figure B, the electron is revolving around this nucleus because of certain amount of force. That force is called a central force or electrostatic force. What is that? The electrostatic force of attraction between nucleus and an orbiting electron constitutes centripetal force on the electron. So here in this orbit, so for example, if you consider this is the nucleus, the electron is revolving around the nucleus. How this electron is revolving around the nucleus? The electron is revolving around the nucleus because of this electrons want to reach to the nucleus. That is the reason there is an attractive force existing between the nucleus and electron. So this attractive force is called as the centripetal force. So what is that? Centripetal force. It is also called as the force between electron and nucleus is considered as electrostatic force. Because of electrostatic force, the electron is constantly it is revolving around the nucleus. If there is no electrostatic force, there is no electrostatic force, the electron won't be run in a proper way around a nucleus. So because of electrostatic force, an attraction forces existed between nucleus and orbiting electron. So this attractive force simply defined as centripetal force. It is also called as the centripetal force. Why? Because the electron is revolving around the nucleus. It means the approachment of electron towards the nucleus. So that is the reason it will be considered as the centripetal force. This is also in terms of other segments. The centripetal force is again it is considered as electrostatic force. Simply it defined as Fe, which is between nucleus, that means proton, nucleus and orbiting electron, and it is equal to whom? So that centripetal force. So that is which is defined as electrostatic force. Before electrostatic force, it is simply the electrons are around the nucleus. This is the reason it is called as the centripetal force. So the centripetal force is simply defined equal to whom? The centripetal force, it is equal to m v naught square by r. The centripetal force is equal to whom? M v naught square by r, where it is equal to whom? So the centripetal force is equal to m V naught square by R. Just recall the central force definition. It is equal to m V naught square by R. That means Fe is what? That means the electrostatic force is what? The centripetal force, which is defined in terms of the electrostatic force, that is m naught square, m V naught square by R. M V naught square by R. Sorry, here I think I mentioned here by 2. M V naught square by R. So this is m V naught square by R. So, but here what is V? V is nothing but what? Linear velocity, which can be considered as, sorry, angular velocity, which can be considered R omega naught. R V naught is considered as what? V naught is considered as R omega naught. V naught is considered as R omega naught, where V naught is the linear velocity of the electron. Where V naught is the linear velocity of the electron. So, therefore, you replace the value. So, what is F equal to? F equal to from the previous slides. From the previous slide, it defined as m V naught square by R. Is it right? Then replace the value. What is the V naught? From the previous slide, V naught is R omega naught. Is it right? Then replace here. What is? M is right. R square omega naught square by R. R will be cancelled. Then it is M R omega naught square. Is it right? So Fe is what? Fe is mr omega naught square. After substitute the value of V, where V is V naught, after substituting the value of V naught, which is R omega naught, then it is mr omega naught square. After applying the magnetic field B naught, an additional force AB acts on the electron. So depending on the direction of the applied magnetic field and depending on the, for your convenience, you can also put the equations. So if you are getting some confusion, then you can use this. You can write this as an equation 1. After applying the magnetic field B naught, an additional force FB acts. The force due to magnetic field, that is magnetic force, that is FB, acts on the electron depending on the direction of the applied magnetic field and depending on the direction of the rotation of electron, because of two conditions. Depending on what? Depending on the direction of the applied magnetic field and depending on the direction of the rotation of electron. So because of these two conditions, what is happening? The force FB either adding or reducing to Fe, means the magnetic force is adding to Fe or reducing to Fe. That means what? That means FB is plus or minus Fe. That you can take as equation 2. Let the centrifugal force, which is acting away from the center. So if the force is acting toward the center, this is centripetal. If the force is acting away from the center, this is centrifugal force. So let centrifugal force is after applying the magnetic field, then what is that? So that is F equal to mr omega square, not mr omega naught. See, this is simply F is the total force. This simply consider net force. The net force due to electrostatic, due to the magnetic field force, it will be considered as F. So here F equal to, what is that? F equal to mr omega square, mr omega square, where omega is change in the angular frequency of electron after applying the magnetic field, where omega is what? Angular frequency of electron after applying the magnetic field. Therefore, the net force on the electron to revolving in a constant moment or in a consistent manner, that is F is Fe plus or minus Fb, Fe plus or minus Fb. But you need to understand what is the Fb. From the Fb is considered as what? The magnetic force due to the force due to magnetic field is what? B naught of minus Ev. What is that? B naught of minus Ev. So after further simplification, we already know what is V. V is nothing but R omega. V naught is nothing but R omega naught. Here V is just R omega. So minus B naught ER omega. Therefore, the above equation, you replace the values of FB and FE in equation 2. What is equation 2? F equal to FE plus or minus FB. So you replace the FE value and FB value. Then what you will get? F equal to Fe plus or minus FB, which will be considered as, see, mr omega square equal to mr omega naught square plus or minus Be r omega. Be r omega. Mr omega square equal to mr omega naught square plus or minus B naught er omega. So for the simplification, what is happening? In the further simplification, so what is that? mr omega square. So r in this r, so will be cancelled. See, that means here in this r, in this r, in this r will be cancelled. So finally, in the further simplification, what we get? M omega square equal to m omega naught square plus or minus B naught E omega. What is that? M after simplification, further simplification, when r is reduced, m omega square is m omega naught square plus or minus B naught E omega. Further simplification is what? M is the common, omega square plus or minus B naught E omega by m minus omega naught square. So this above equation, again for the simplification where m is the common, then omega square equal to is what? So this is just like we change into polynomial equation, polynomial. So whenever it is changed into polynomial, a square, b square, sorry, whenever it is changed into polynomial condition, omega square plus or minus B naught E omega by by m minus omega naught square equal to 0. So now just take here one assumption in the place of omega, that is omega naught plus del omega. So what is the condition? Just consider a condition. Why here the question is, somebody is asking why we need to replace here. So here the frequency is changing, it may be reducing, it may be increasing, or it may be decreasing, because that's particular condition there we are taking the changing of the frequency. So that is the reason in the place of w naught plus del omega is replacing. So after that delta omega and delta omega square both will be neglected. So in the further simplification, omega square plus, this is the a plus b whole square, omega naught square delta omega plus 2ab plus, after simplification, see here b naught e by m into del omega will be neglected. Why? Because del omega is less than to the omega naught. In the similar way, the combination of b naught e by m into delta omega is very negligible. That is the reason it is neglected. So here in the place of w naught plus delta w is replaced, then it is a plus b whole square formula. In the further simplification, omega naught square plus del omega square plus 2 omega naught delta omega, and this plus or minus b naught e by m into omega naught plus b naught e by m into delta omega, where delta omega is negligible. That's the reason the entire concept, the entire factor is also neglected. So here what is happening, you can see here omega naught will be out. Then finally what will be there, you can see here after neglecting delta omega again, then what you will get. So that will be after neglecting delta omega square, it will be 2 omega naught del omega plus or minus b naught e by m into omega naught. So for the simplification, so it will be considered as what? 2 omega naught del omega plus or minus b naught e by m into omega. Therefore, del omega is what? Del omega is what? Plus or minus b naught e by 2m. Plus or minus b naught by m. See, you can see here. So, what is that? So here 2 omega naught 2 omega naught del omega equal to b naught plus or minus e by m into omega. See, omega will be out. So del omega is what? Del omega is b naught e by 2m. So del omega is what? Plus or minus b naught e by 2m. So because of this del omega, because of the magnetic moment mu L, the change in magnetic moment del mu m. So mu L is nothing but magnetic moment. The change in magnetic moment is what? Delta mu n. So the change in magnetic moment delta mu n for the change in angular frequency. So due to the angular frequency, whatever magnetic moment is generated, that can be considered as what? So from equation, uh, what is mu L? Mu L is nothing but this is minus E omega naught r square by 2. This is about the mu L minus E omega naught r square by 2. This is mu L, and delta L is delta omega is what? Del omega is what? Plus or minus b naught E by 2m by replacing this value. So see here in the place of not change, only we are using del symbol here. The del mu L is what? E r square by 2 into omega, that will be simply considered as, see, e minus e r square by 2 into omega, that will be considered del omega. See here omega not that, but here it is considered as del omega. So here omega is omega not here in this condition. So here del omega delta omega. So here del omega. So replace the value of del omega. So what is del omega? B naught e by 2m. So minus 1 by 2 e r square b naught e by 2m. After further simplification is what? 1 by 2 into 1 by 2, that is 1 by 4, minus e square r square by, sorry, minus e square r square b naught by 4m, which is del mu L. This is called as what? This is simply called as the change in magnetic moment. The change in magnetic moment is what? The change in magnetic moment is what? Minus e square r square b naught by 4m. The induced dipole moment has a direction opposite to the applied magnetic field. So you can see here that is the minus symbol. That simply consider applied to, it will be simply considered as opposite to the applied magnetic field. The magnetic moment induced when a pair of electrons have opposite rotation considered as what? So this is when pair of electrons are taking. So the pair of electron opposite nature is in the rotation is considered as what? It is considered as mu L minus del mu L of plus minus mu L minus del mu L, which is considered. So here you simply analyze here what it is considered. It's simply considered as, so here mu L will be cancelled. So minus del mu L minus del mu L is there, that is minus 2 delta mu L. Is it right? So mu L minus mu L will be cancelled. Minus del mu L minus del mu L is there, that is minus minus, that is minus 2 delta mu L. This induced magnetic moment is in the opposite direction to the B naught. So here you are getting minus symbol. So this induced magnetic moment is in the opposite direction to the B naught. This is the property of a magnetic material. So we already know what is diamagnetic material. The diamagnetic material feebly repel or weakly repelled by external magnetic field. So it is, that means, in the opposite direction. So here minus symbol is there, so which is indicating opposite direction to B naught. So this can be considered as a property of diamagnetic material. Diamagnetic atoms have more than one electron and the orbit are also not circular. So here diamagnetic material, it is a spherical shape. Diamagnetic material have more than one electron and the orbits are also not circular. Suppose let us consider a spherical one. This is not a circular one. It just look like a spherical shape. So diamagnetic material more than one electron, and but it is not on that one. It is also having one electron but not in a circular one. It look like a spherical shape. For example, let us consider a spherical one. In the spherical shape, let us consider three integer factors, three directions, that is x, y, z. So in the spherical shape, let us consider three directions. So that is Rx, Ry, Rz are the average values of the radius of the electron. So that is Rx, Ry, Rz are the average radius values of the electron along the directions of x, y, z. Then the radius of atom is considered. So the overall radius of atom is what? Along with the x, y, z direction, x, y, z directions, it is considered as R naught. So here that is considered as what? That is considered as R naught square equal to R in x direction, R square in x direction, R square in y direction, R square in z direction. So R naught square equal to r x square, r y square, r z square. So this is about the r naught, our total radius of the total radius of the spherical shape in x, y, z square, that is r naught square. R naught square equal to r square, rx square in x direction, r square in y direction, r square in z direction. Also consider as, it also considers whom, if it is the b is directional to the z, then sometimes it is considered x is equal to y, y equal to z, then r square x, r square y, r square z are equal to r naught square by 3. Why? Because 3 is a 3. Why we got 3 here? Because it is indicating the 3 direction characteristics. So the average radius of the orbit along the xy directions is, if it is the average radius of the orbit along the xy direction, consider as due to the spherical shape, and when the magnetic field B acts along the z, when the magnetic field B acts along the z direction, so conditions you need to consider due to the spherical shape, and when the magnetic field B acts along the z direction, the average radius of the orbit along the xy directions, xy directions is what? It is considered as r square equal to, it is considered as r square equal to rx square plus ry square, which is 2 by 3 r naught. So here it is a spherical shape one, first condition. Hence along the xy directions, when magnetic field B is along the z direction, it is considered what? That is r square equal to r square x, r square y, which is equal to r naught square by 3 into 2. So here when magnetic field B acts along the z direction, that is r square equal to r x square, r y square, which is equal to 2 by 3 into r naught square. Suppose the diamagnetic substance contains n atoms. Suppose The diamagnetic substance contains n atoms per unit volume and each atom has Z electrons. So the number of electrons are what? Z. And number of atoms are what? Per unit volume is what? N. Then the induced magnetic moment per unit volume, that is mu induced, is considered as what? That is considered as mu induced is considered as plus nz delta mu l. You need to consider this is delta mu l, del mu l. So nz is there, then in the place of del mu l you replace the value. What is that? E square into b naught into r. What is r? R is nothing but r square is nothing but what? 2 by 3 r naught. 2 by 3 r naught. 2 by 3 r naught square. In the place of r you replace. What is delta mu l? Delta mu l is nothing but, what is delta mu l? Delta mu l is nothing but what? Minus e square r square b naught. Just remember. So replace here. Then what you are getting, that is a square 2 by 3 r naught square b naught by 4 m. After further simplification it is minus nz e square r naught square b naught by 6m minus n z e square r naught square b naught by 6m. So this is about the the change of the dipole moment. So this is where r is, you consider what? R you consider from the spherical shape concept, that is r square equal to what? R square x r square y, which is 2 by 3 r naught. Is it right? So replace here. But what is the b naught? B naught is nothing but b is proportional to h. Sorry, b is proportional to h. Then b naught is what? Mu naught h. Therefore, you replace the value of b naught, which is again considered as minus nz mu naught, where you replace the value here. B naught is mu naught h. Mu naught h e square r naught square by 6m. So this is about the induced magnetic moment. Then what is the susceptibility? The susceptibility of the diamagnetic material considered as what? That is chi equal to mu induced by h. What is that? Mu induced by h. Mu induced by h. What is the value of mu? So the value of mu is, the value of mu is what? This is the value of mu minus nz mu naught a square r naught square by h by 6m. So susceptibility is what? Mu induced by h. H will be cancelled, and finally what is the term remaining? That is minus nz mu naught e square r naught square by 6m minus nz mu naught e square r naught square by 6m. So from the above equation, this is above the susceptibility. From this above equation, the susceptibility is negative and small. So you know very well which material having small susceptibility and negative susceptibility. Yes, that's right only. That is diamagnetic material. So now this we simply consider as theory of diamagnetic material. It's simply called as theory of diamagnetism, and it is proposed by Langevin. So it is called as Langevin theory for diamagnetic material, and this theory is explained on the basis of the classical mechanism. So it is also called as classical theory of diamagnetic material. So, and finally you can also say, we in this equation we never found temperature concept. So we can simply say that one, the susceptibility of diamagnetic material is independent of temperature. What is that? Independent of temperature. So simply we can consider. So this is the concept of the Langevin theory, which is explained on the basis of classical theory, which is introduced in 1905 by Paul Langevin. So this is about the diamagnetism or Langevien theory for Langevien theory for diamagnetism or classical theory for the diamagnetism. So we can also say that one. So here the susceptibility is proportional to the n, the susceptibility is proportional to the z, the susceptibility is proportional to the mu naught, the susceptibility is proportional to a square, the susceptibility is also proportional to r naught square, but the susceptibility is inversely proportional to m. This is also one of the conclusions we need to give here. So this is about the Langevin theory. So Langevin theory is nothing but in the year 1995, Paul Langevin is introduced this concept to explain the diamagnetism nature, diamagnetic material characteristics, which is nothing but diamagnetism. So this theory totally explained on the basis of the classical theory. So sometimes, it is also called as, not sometimes, it is also called as classical theory of the diamagnetism. Thank you.